for your kind attention.
Now we're open for a question. So I actually noticed one of your earlier studies on this iron silicon, some kind of amorphous alloy by drawing it.
Oh, that's amorphous wire.
Right. So
Yes.
the alloy initially has zero ductility, but when you draw it, cold draw it, then you get 3 or 4%.
Yes.
Do you think you can apply that to
Yeah,
mechanical process? Because one of the problems is ductility.
Yes, I think that after so heavily cold loading for the BMGs, we can notice, we can recognize the increase of the ductilities. But this one is that we can get almost 90% cold reduction. It's impossible to give such a significant cold reduction to BMG. And also very important too, that's the drawing. Drawing that generates compressive stress.
Compressive stress.
Yeah, that's important. Just cold rolling, I don't think that's a good way to increase the ductility. Cold drawing is good.
It's still too brittle. Professor Lee.
Well, I know you have coupled theory and the rules try to describe the glass formability, right? Can you tell us why aluminum-based alloys are so difficult to make a bulk metallic glass, right? Any simple reason to explain this kind of behavior? So far, we cannot make a BMG with more than 1 millimeter size of aluminum-based material.
Yeah, in my case, 0.7 millimeter thickness is a maximum. And recently, some Chinese groups reported 1.5 millimeter or something. Anyway.
Not true.
Anyway, that's the very puzzling problem, and that's a very important point. You know that aluminum, that's the alloy composition, is aluminum 85 or something atomic percent. When you look at the equilibrium phase diagram in aluminum, layers, lanthanoid or something, is not does not agree with the eutectic point. Very large so-called mixed phase, liquid and solid phases. So if we can find the new alloy compositions with a real eutectic, near the eutectic point, probably I can get that large scale of bulk glass. But in that case, alloy compositions deviated from aluminum-rich composition. That's it. So one example, zirconium, aluminum, nickel. That's the first. We found aluminum, zirconium, nickel glass alloys. Shows the glass transition. Then so we just examined it. Then so to find appropriate compositions exhibiting the large glass forming ability or wide supercooled rig, then approaching that's 10% aluminum or 15% aluminum. So aluminum rich alloys are very difficult. The reason why, main reason is that the large temperature intervals or mixed regions of solid and liquid phases. I think that's 300 or sometimes 300 or 400 degrees also. That's one of the reasons. Another, that's the, that's probably, that's the main reason, I think.
So when you realize the coating system using the HVOF process, so what's the temperature you use to maintain the glass
we used that's very low temperatures.
Okay.
We controlled the temperatures nearly the glass transition temperature.
Okay.
We didn't heat up.
Okay. So what's the major reason for improving the mechanical
high
property?
velocity.
Yeah, I know the HVOF, but what's the main reason for the mechanical property enhancement after the coating system? So you show a slide with the coating system.
We just so in the application field, which requires a compressive stress field, something. Not the if we tested in the tensile stress field, I don't think we can get the good. Anyway, we didn't. Just compression.
Okay.
That's okay. Wear resistance or corrosion resistance or something.
Okay. Thank you.
Is it possible that in some of these apparently amorphous systems, you have actually very big unit cells? So do you use, for example, small
Not
angle?
unit cell. Okay. Anyway, medium. Okay. Yes. Okay.
So maybe sometimes if you check it with a small angle, X-ray diffraction, you might see some very large periodicity in the structure.
Well, so I didn't. We didn't apply that the small angle scattering to. Yeah, long time ago. So for aluminum-based alloys, at the first stages. So aluminum-based amorphous alloys has many interesting points. That's at the first stages, like the spinodal decompositions or something. We used the small angle X-ray scattering techniques. But bulk glassy alloys, we didn't apply that.
There's no feature. I mean, sometimes there's some small angle, but there's no appearance.
Yeah.
Okay.
I have a question, actually two. How to cool the material fast cooling 1 million degrees per second. And the second thing is how to make your research into a commercialized product.
You mean that the very high cooling rate of 100 million, no, not 100, 1 million Kelvin per second.
Yeah. I see there is cooling rates, different cooling rates, right?
You mean the different, that's of course, depending on the alloy composition. That's the cooling rate. That's so critical cooling rate for glass formations depends significantly on the alloy composition. So it's very important to find the alloy compositions with low critical cooling rate. So that's for instance, we can get, I think that's 8 centimeter in diameter. That is 0.02 or 3 Kelvin per second. That is enough. But that's iron silicon boron amorphous wires. We need the 100,000 Kelvin per second. That's depending on the alloy compositions. And the second question is, what is that?
I have a question. How to cool it? What
How
machine?
to cool?
Yeah, is that a laser cooling or a
No. I used okay. So I didn't explain what is where. Where is that? Yeah, that's for instance this. This is for instance. Can you imagine that? That's the drums rotating. That's the water. Water is put into the rotating drums. So water layers is formed by centrifugal force. So when the molten alloy is ejected through the nozzles, that's usually 0.1 millimeter nozzle diameter. So we can get the amorphous wires. You can see that the amorphous wires here in this part. Scarcely we can. Anyway, that's the, so we can, in this case, we can get the almost, I think, 1 million Kelvin per second. We can get the high cooling rate. When we, it's important point to control that the diameters. If we increase the diameters to over, anyway, 150 micrometers, 0.15 millimeter, we cannot get, we was not able to produce the amorphous wires, very brittle and crystallized. That's the critical diameter or critical thickness is very important. So if you reduce the critical thickness to about 20 micrometers, you can get the very high cooling rate of about more than 100,000 Kelvin per second.
Okay, one last question. Okay, I'll give it to the student.
Check.
You're the last one.
All right. All right. For your paper about molecular dynamics simulations, how did you model the medium range order in liquid metallic classes, in metallic classes?
So I didn't, I'm sorry, I didn't do myself just molecular dynamics so simulations. But that's we use so-called first principle. So that's the calculation method by these collaborators, Dr. Takeuchi. He studied that he got that structural data based on that I think that's the polyhedral cluster models, and they modified by using the computers and many steps, and then so after relaxation they got that so-called internally equilibrium metastable state. They got that. So structures include the short range or medium range atomic configurations. That's
Yeah, thank you. My question is very short. So when I just take a look at this picture, an idea comes to my mind. So in contrast to making metallic glass big, so I'm wondering how small the smallest size of metallic glass can be.
Smallest size.
Yeah. So for a wire.
Oh, wires.
Yeah.
Wire is that's the. I don't. Anyway, as gas state, 100 to 120 micrometers. Micrometers. Then we can hold down to 15 micrometers.
15.
Cold drawing.
Okay. Is there any like size limit for metallic glass?
No, I don't know that. Depending on the ability of eyes, we were not able to identify. 0.015 millimeter is very difficult to identify. This is you can see that this is also we can see scarcely we can see that wire. Anyway, too fine to identify. Of course, that's if we use that optical microscope or something. Under the microscope, we can recognize, but that's just very difficult to identify. I believe that the wires is 15 micrometers. Of course, by using the deposition techniques, you can get the very thin amorphous. I think that in that case is 50 nanometers or something by sputtering. But quenching techniques do not give us that very thin one.
Okay, thank you. Yeah, because I just saw that the surface atom is very active when the size is going to very small. So the atom maybe...
Yes, that's right. But the amorphous. But it's very important to form the passive surface layers. by controlling the alloy compositions. Otherwise, that's a very, very corrosive state. It's not useful for application.
Okay, I think I'm going to close. We have a little gift to present it to Professor Inouye.